Hello, and welcome to your lesson for today. We are going to be working through electron dot structures. So you should be, I believe, if I recall, on page 6. Let me just check that. Yes, you are on page 6 of your notes if you're following along with me. All right, so here we go. Today, our learning objective is to be able to construct electron dot formulas to illustrate specifically covalent bonds. You will be writing your chemical formulas for the compounds as well as we're working through them, or at least recognizing them as you're going through these. Your success criteria to know that you're being successful in today's lesson. You will accurately draw electron dot structures for covalent compounds. And so let's go ahead and get started. So we're going to first start by making sure we understand our octet rule. So we're going to do a little think for a moment. I want you to pause this and discuss with your elbow partner and write down your thoughts. What do you remember about the octet rule? What does that mean to you? Go ahead and pause and make a quick note. All right, so the octet rule, just as a reminder, is going to be an atom's preference for having 8 valence electrons in its outer shell, in its valence shell. Atoms with more or less than 8 valence are going to participate in a chemical bond in order to attain that octet. If you guys will recall, in this first part of the picture here, you can see the transfer of electrons. This is for our ionic bonding, right? So ionic. And then here in the bottom, if they are sharing, that's for our covalent. Okay, so just a quick reminder. And then this rule is applying to our S electrons and our P electrons from our electron configurations that we learned about before. All right, so here we go. We're going to be talking about structural formulas. So what this does is it uses letter symbols and bonds to show the relative positions of atoms. We are able to predict their structural formula by drawing what we call Lewis structures or electron dot structures. So as you guys saw in the notes yesterday, we can have dots that represent a bond, or we can have lines that represent the bond. Okay, so we're going to define a few things here. If you've got some empty space on your paper to kind of make a couple of little notes here, this slide's got some important information. So this element in the middle, the one in the center, if there is a central atom, that's what we'll call it. We'll call it the central atom. This is the one that is bonded to all the things around it. And so we'll call that our central atom. Elements on the outside that are not central atoms, we call these terminal atoms. Just like when you go to the airport and you go to your terminal, you're on the outer edges of the airport. We don't have terminals in the middle. Airplanes can't get to the middle, right? So we call those our terminals or our terminal atoms on the outer edge. Ones like bromine, this diatomic bromine here in the middle, notice they just have 2 elements, so there's not really a central atom. They're just going to sit next to each other in that particular instance. Okay. So the next little box, 1 pair of dots or 1 line is equal to 2 electrons. We covered that in our notes yesterday, but I just want to make sure that we are all very clear that I can either represent a bond by a pair of dots or 1 line. They mean the exact same thing. All right, and then I also want to go ahead and define dots that are not participating in a bond. So they have a name as well. They're called lone pairs. All right, and so anytime we're talking about lone pairs of electrons, these are ones that already came with the element. So they came with their valence count, and we're going to give those back to that element. They are not they're not participating in a bond. They're called lone pairs of electrons. And we'll look more into that a little bit later. Okay, so let's get into the steps. As you can see, there's 6 steps to drawing our structural formulas. It may seem like a lot of writing, like a lot going on here, but it's really not that bad once I show you examples, okay? So I'm going to go ahead and go through the steps with you. If you need to pause to fill in some blanks, you can do that now, and then listen to me while I'm working through them, okay? And I'm going to work lots of examples with you, so we're going to get this down really well, okay? All right, so step 1, count the total number of valence electrons. So you're going to do this count for every single atom in the compound, okay? Determine the central atom and write its elemental symbol. Place your terminal atoms. Step 3, place their elemental symbols around the central atom. Step 4, place one bond between each terminal atom and the central atom. And then we're going to actually subtract that number from the total electrons that we got in step number 1. So our goal is to keep a count of our valence electrons to make sure that we keep up with all of them and we utilize all of them. If I don't use them all, then one atom somewhere is more than likely not going to get its octet. Because remember, that's our overall goal, is for all of these atoms to end up with an octet via sharing, okay? And then number 5, add lone pairs to the terminal atoms to ensure they get their octet. So after we've bonded, we'll continue to add on lone pairs to give them their octets. And we're going to keep subtracting that from our total count. We're going to keep track of how many we have left. And then step 6, add any extra electrons to the central atom to complete its octet. So the central atom will get its lone pairs last if it needs them, okay? And so as you guys saw in the notes yesterday, we looked at how many bonds different elements can make. Typically, our element with the most bonds that it's able to take on, that one's typically going to be in the middle. That'll be our central atom. Another thing we can think about is the one by itself is also typically going to be in the middle or in the least quantity. So we're going to go ahead and we're going to start applying these rules to our, come on, where'd it go? I don't want to click. There we go. We're going to go ahead and apply these rules to our couple of examples we have. We have carbon tetrabromide here, CBr4, and we have nitrogen trifluoride here, NF3. We're going to work through all the steps on each of these examples, and they'll probably make a lot more sense. All right, so for carbon, I have 4 valence electrons, okay? And then for each bromine, I have 7. All right, and that's times 4. So 4 times 1, 7 times 4, so carbon is 4. And then this is 28. And so what I have is 32 electrons to work with, okay? And so what we want to do is we always want to keep our count first so we know how many we're working with, okay? So that was step number 1. Not hard. You guys know how to find valence electrons at this point, so it shouldn't be a big deal for us. But notice that whatever their subscripts were, I multiplied those out by my valence, okay? So step 2, our central atom. So our central atom is never going to be a halogen at this stage in your chemistry career. When you get to AP or get into higher level chemistry classes, the halogens do other things. But for now, halogens will never be in the middle, okay? And so they'll always be terminal atoms. And carbon, since we learned yesterday that it can bond 4 times, carbon's going to be in the middle. All right, so it's kind of like our little monkey in the middle. We're going to put carbon in the middle, and then we're going to put bromines on each side of it like this, okay? And so that's really step 2 and 3 is identifying your central atom and sticking it in the middle, and then identifying your terminal atoms and putting them around it, okay? Step 4, we're already on step 4. Look at that. We're going to get one bond between each of them, okay? So we're going to go 1, 1, 1, and 1. Everybody gets a single bond, okay? Now, we're going to keep count of how many electrons we just used, and we're going to take that away from what we did in step number 1. So 2, 4, 6, 8. Remember, each line represents 2 electrons. So we're going to subtract 8, and we're going to be down to 24 electrons, okay? And so we've got 24 left to place, and we're moving down into step number 5. Okay, so it says add lone pairs to the terminal atoms. Okay, so we know that each bromine came to the compound with 7 electrons total, right? That's its valence. And one of them is participating in the bond. Okay, so each of these bromines are still owed 6 more electrons. Okay, so we're going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, and that actually took care of the rest of my electrons, and so I should end up with 0 at the end, so I know that I accounted for all of them. Okay, and so I don't have any more to put on my central atom, and so I didn't end up needing any more either, okay? Because when your last job on here is to keep count, okay, of each atom's electrons and make sure they each have their octet, okay? Remember, an octet is 8, so bromine has 2, 4, 6, 8. This bromine has 2, 4, 6, 8. This one has 2, 4, 6, 8. And 2, 4, 6, 8. So each bromine has 8, and then we already counted that carbon had 8 around it. So everybody has their octet. This is a completed carbon tetrabromide compound, and that's it. Okay, so we're going to go ahead and try that again on NF3. If you feel like you want to try this one on your own, you're welcome to pause and try it yourself. And then go ahead and come back in here and see how you did. But I'm going to go ahead and start on that one. All right, so just like I did before, we're going to count our total valence electrons. We're going to start on step number 1. So for nitrogen, each nitrogen has 5, and there's only 1 of those, so I have 5 total from nitrogen. And then each fluorine has 7, and there's 3 of those, so that's 21. So I have 26 electrons to work with total here, okay? I'm going to determine my central atom. Nitrogen can bond 3 times because it has 5 valence electrons, and I'm trying to get to 8. Fluorine can bond once, and so nitrogen is my logical choice to be in the middle. And then I'm going to place 3 fluorines around it, and it really doesn't matter where you place them. I'm going to go ahead and do this. Like that. All right, so I got my central atom and my terminal atoms. All right, the next step is to add a bond to everybody, okay? Connect them all, all right? So all to the central atom, that is. 1, 2, 3 bonds, all right? And that's 2, 4, 6 electrons. So I'm going to take those 6 electrons away from my total, and I'm going to be down to 20 electrons left. So then I'm already down to step 5, add lone pairs to those terminal atoms first, right? And so just like bromine up in the last example, each fluorine is going to get 3 pairs. 2, 4, 6, 8, 10, 12, 14, 16, 18. So I just used up 18 electrons, and now I'm down to 2. So each of my fluorines right now have 8 electrons around them. They have an octet. They are good to go. However, if you look at this nitrogen still only got 6, and I got 2 electrons left. So those 2 electrons get to belong to nitrogen like that. So nitrogen now has a lone pair and 3 bonds which is what I think we would expect here, because remember, a nitrogen would have 1, 2, 3, 4, 5 electrons, right? And so it already had a lone pair whenever we were originally looking at nitrogen, and so it would have those 3 places to bond like it does here with fluorine. All right, and that's really all there is to this, guys. You're just drawing and counting, okay? We're going to go ahead and we're going to clear, and we are going to be doing some more on the next slide. Oh, whoops, got to do exceptions. Okay, exceptions to the octet rule. So if you haven't figured out, in chemistry, we have lots of exceptions. We make rules, and then we find elements or substances that break the rules. So here we are again with our rule breaking. So we have different elements that we consider electron deficient, okay? And a deficit or a deficiency is when they have less than expected, okay? So some atoms have fewer than 8 valence electrons, but they still get to be considered stable. And you've actually already been exposed to this, and it didn't bother you at all, because we have ones like hydrogen. So we know that hydrogen is in level 1, and that it's only going to get 1 electron ever. And so its octet is considered to only have 2 total electrons. So hydrogen will only ever have, it will only ever have 2 electrons total, which equals 1 bond. Okay, so hydrogen only gets 1 bond, and it will have no lone pairs. Okay, it is perfectly satisfied with just 1 bond, no lone pairs. You can see here in this example to the right, this hydrogen has 1, this hydrogen has 1, and they will share those 2, and they are perfectly satisfied just like that. So hydrogen never has lone pairs, only ever gets 1 bond, never double bonds, never triple bonds, okay? The other one that we want to consider is boron. Boron is a unique character in that it has 3 valence electrons, right? So boron only has 3 dots normally. And what it will do is it will bond out those 3 dots into full-blown bonds. Boron will not have lone pairs, okay? So no lone pairs. All right, and 3 bonds total. So these guys are exceptions. You guys can see here, boron trifluoride, BF3. Notice this one has no lone pairs. So we just did that one with nitrogen just a few minutes ago. And notice it had lone pairs, but this one does not. So just keep that in mind, that these are exceptions to the rules. And so they are not going to follow what we would typically expect. Their octets look a little bit different, okay? All right, so sometimes when we're trying to satisfy our octet rule, we don't have enough electrons. Once again, we have another situation of electron deficiency. So if I don't have enough electrons for all atoms to get their octet, we have opportunities for them to share more. And we've talked about double and triple bonds already in our unit. And so if I don't have enough when I'm drawing, I can look for opportunities of elements to bond multiples, okay? And so I can have 2 pairs shared to form that double bond, or 3 pairs shared to form a triple bond. We've gone over this once before. And I want you to make a little side note, okay? Somewhere on your page, there's 5 elements that can double and triple bond, and it's carbon, nitrogen, oxygen, phosphorus, and sulfur, okay? These are actually the only 5 elements that can double and triple bond with each other, okay? They can't double bond with anything else. Only these 5 can bond, once again, with one another. So 2 carbons can double bond, or a carbon and an oxygen can double bond, carbon and a phosphorus could triple bond, carbon and sulfur, nitrogen and sulfur, whatever combination you want. But these are the only 5 who can do this with one another, okay? So make that little note. We call this the CNOPS group, okay, as you can see, CNOPS. And so just make a note to yourself. These are the only ones who can double or triple bond. Okay, little side note there. And that's going to help you out. Okay, all right. Oops. All right, so we're going to go ahead and we're going to draw some more. And we're going to follow those same 5 rules. It says draw the following molecule, identify the number of lone pairs, the number of bonds, and the number of electrons involved in bonding. So we're going to be working through these examples together. We've got another page of these. Hopefully after we work through all these questions, you're going to feel super confident in the content. If you want to try these on your own without me, please feel free to pause, but I am going to work through all of them with you, okay? All right, here we go. So carbon has, oops, let me use my pen. Let's change to green. We'll go green for a bit. Okay, so carbon has, clear screen. We'll try that one more time. Carbon has 4 times 1, so that's just 4. Chlorine has 7 times 4. Oops. So that's 28. And so I've got 32 electrons to work with, okay? And so that actually fixes the last thing that was asked for. I know that carbon can bond 4 times and each chlorine can only bond once, so it makes sense to put carbon in the middle and then each of my chlorines around it. All right, so then everybody gets 1 bond. And I just used up 8 electrons. So we're going to subtract 8. And we're going to get 24. And then I've got to go ahead and place my electrons, my lone pairs of electrons around my terminal atoms, because right now each terminal atom only has 2 electrons. My carbon is actually good to go. It's already got 8. But each of these chlorines needs its 8 total as well. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, so minus 24, and I have accounted for all of them now. So it also asked me to identify the lone pairs. So that's one set of electrons not bonded. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so I have 12 lone pairs, and I have 1, 2, 3, 4 bonds. Okay. And so that's all that's asking for. You're just counting. And we're going to do this as well on your homework packet. All right, we're going to go and do bromine. Bromine is 7 times 2. And so that's going to be 14 electrons total. Since they're sitting next to each other, we're just going to do this. There isn't really a central atom. We give everybody a single bond. All right, minus 2. And we're down to 12. Well, each bromine still needs its lone pairs. So 2, 4, 6, 8, 10, 12. And that took care of the rest. All right, and hopefully you're starting to notice a pattern. You notice that all of our halogens end up getting 6 electrons around them. So let's see, we have 1, 2, 3, 4, 5, 6 lone pairs and 1 bond. All right, we'll go ahead and move down here to HCl. Hydrogen just has 1. Chlorine has 7, so that's 8 electrons total to work with. And we're just going to place them right next to each other. Everybody gets a bond. So we're going to subtract 2. We're going to be down to 6. All right. So remember, hydrogen is one of those exceptions to the octet rule. So hydrogen is actually just fine, satisfied, needs no more because it already has its single bond right here. So those other 6 are actually going to go on my chlorine like that. All right, and everybody's set. We've accounted for what we need to. So I have 3 lone pairs and 1 bond here. Okay, we're going to move a little bit quicker. Hydrogen is going to contribute 2 total because H is 1 and there's 2 of them. And oxygen contributes 6, so I'm going to be back at 8 on this one as well. We're going to put oxygen in the middle. Now, I know you probably want to put hydrogens on either side, but I want you to actually put them 90 degrees from one another because this is actually going to help us out a little bit later when it comes to the shape. So hydrogen, 1 bond, hydrogen, 1 bond, so minus 4 electrons. I'm down to 4 left. Remember, my hydrogens are good to go. They don't need any lone pairs, so those are going to go actually on my oxygen because remember, oxygen has 6 valence electrons originally, so we've got to give it its extras that it deserves. And so here we'd have 2 lone pairs, 1, 2, and 2 bonds, like that. All right, we're going to go and go on to our next page. Let me go back. There we go. Okay, once again, if you want to pause, you're welcome to try these out. Before I do, hydrogen has 2. Whoops. And sulfur has 6. So this one, if you'll recall, oxygen and sulfur are in the same family, and so they're going to have similar chemical behavior. So what's really cool is that if I knew that oxygen did what it did, then sulfur is going to do the exact same thing. So we're down to 4, and sulfur gets its lone pairs just like oxygen did, and that's going to use them up. So this is actually going to look just like our water. We just changed who our central atom was. All right, 2 lone pairs, 2 bonds. All right, next we're going to work on, let's do pH 3 next before we go across. So phosphorus has 5. And each hydrogen has 1, so that's 3, 8 total. We're going to put phosphorus in the middle. Hydrogen is never a terminal atom, is always a terminal atom, just like our halogens are. All right, so phosphorus in the middle, and it doesn't matter where you put your hydrogens. I'm just going to put mine there. Everybody gets a bond, 1, 2, 3, so 8 minus 6. Is 2 left. Remember, our hydrogens get no more. They are completely satisfied, so therefore that lone pair is going to go on phosphorus. And this looks very similar to what we did with nitrogen, once again, because phosphorus and nitrogen are in the same family and they're going to have the same chemical behavior. So once you figure out one central atom and how it works, you get really good at guessing at what the other ones are going to look like. So we have 3 bonds, there we go, and 1 lone pair, like that. Okay, this next one gets a little more complicated. Okay, these next 2 actually. So carbon has 4, and each oxygen has 6. 6 times 2 is 12, and so we're going to have 16 electrons to work with. Carbon is in the middle, and we'll put our oxygens on either side. All right, we'll put a single bond like this, and that's going to take care of 4 of our electrons. So now we're down to 12, okay? And so here we're going to do And just be prepared to erase some things, by the way, because we're going to have some adjusting to do on this particular one, but I want to walk you through the thought process. So if I have 12, I'll put them on my terminal atoms. Oxygen gets 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so I pretty much just used them up. And it looks like it's about to end my recording, so I may have to start a new one here in just a second. Okay, well, I guess I'm going to have to start this carbon dioxide one over. That's okay.